Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So it's either week 3 or the rain is stopping people coming. Oh, it must be week 3. Yeah. All right. Okay, so what we're going to do today is we're going to start to move on through talking about describing distributions. Okay, so what we have in mind here is, so most of you know the assignment is coming up, and so this is sort of moving us towards being able to do that. So I've had a few emails already from people who are starting the assignment. My best advice is wait till we cover a bit, otherwise you're going to do it wrong or badly. And you'll understand what I mean by that in a second, because there's an art to doing simple things well. And you need to do simple things in the assignment, but you need to do them in a particular way in order for this to work properly. So if you're worried about the assignment, don't, okay? It's not long. We should have at least a week to do it, right? Which is plenty of time. It shouldn't take more than a couple of hours to do in total. And if we run short of time, I'll move the due date, right? So relax. We're headed in the direction of being able to do it. And don't worry too much, okay? All right, so last week when we finished up, we were talking about this sort of one-dimensional distribution of a particular data set. Remember this intermediate star data? These are the stars that aren't moving too fast away from the galactic plane but aren't moving too slowly away from the galactic plane. Okay? And so they're sort of, we don't know whether they're disk stars or halo stars. So we're calling them intermediate stars, and we're trying to characterise the distribution. Now, the end game for us is going to be able to say, look, the distribution of these kinds of stars looks like this, and then we're going to hope to compare that distribution with the distributions for the other types of stars. Remembering that the heart of good decision making and good statistics is making valid comparisons. That's where we're headed. So this is the one-dimensional scatter plot, which is a really simple plot. And let me be very clear about this. We're going to talk about a number of different types of graphics, but some of them you'll never actually use, right? So here what we're focusing on is not the destination. The destination will be certain graphics that are very useful, but the journey, right? How do you get to those useful graphics, and what was the thinking in behind it? And so this is a very simple graphic. It doesn't prove to be particularly effective because you get points that are sort of sitting right on top of one another. You don't get a good sense of how close those points are to one another because they're all sitting right on top. And so we're going to try and fix that. Now, one way to do that is to use that second dimension. Now, it's a one-dimensional scatter plot, but we're plotting it on a two-dimensional surface. And so what we're going to try to do now is use that second dimension. Did a very simple thing with that last week by jittering, introducing randomness into that second dimension. Now what we're going to do is we're going to introduce something more meaningful. And that meaningful thing is that if 2 points are sitting right on top of one another, we want to just stack them up. Okay? So push one up above the other one. And if there's 2, we'll stack them up twice. Okay? Now to do that, I've written a function in R to do that stacking. And the reason I've written a function to do it is twofold. First, there's no function in R that already does it. And second, I want to show you a simple function and how it works. And we're going to talk about some of the features of functions that are useful if you're going to be writing your own. So the function is called stack, and it's over here. So we're going to run through it. I'm going to tell you how each part works. Again, it's not a function I expect any of you to actually use in real life, but the goal is to learn a little bit about how functions work. Okay? So if you look in that top left corner, So the form of a function is you give it a name, so I'm calling this function stack, and then to tell R that you're writing a function, you go stack equals function brackets, and then inside those brackets, you put the inputs to that function. So this function is going to accept a single input, which is x, a vector of data. And then, next line, you put a curly brace. And that tells R from then on, you're in the function. Now, what we do in the function stays in the function. Have you ever heard that expression, what happens in Vegas stays in Vegas? You heard that expression? It means if you go on a holiday in Las Vegas and you get up to all sorts of naughty stuff, no one knows, right? Because what happens in Vegas stays in Vegas, okay? Because Vegas is called the city of sin, gambling and stuff like that, okay? So what's the relevance of this? Well, in R, what happens in functions stays in functions, okay? Anything you do inside a function only lives inside that function, not outside. So, first thing I do in this function is I go x equals sort x. So that takes x, sorts it from smallest to largest, and then puts that back into x. Now, that's happening inside the function. That x thing, outside the function, stays as it was. Inside the function, it's been replaced by its sorted values. So if x was a vector which was 3, 2, 1, inside the function it becomes 1, 2, 3. Outside the function, it stays as 3, 2, 1. What happens in functions stays in functions. Okay? Now there's a technical computing name for this. It's related to what's called lexical scoping. In other words, what objects are in different environments changes depending on the environment. So if you're inside a function, you're referring to things only inside. Okay? So x is replaced by sort of x. Y is going to be a vector of zeros whose length is the same as x. So I go y equals repeat. I want to repeat 0. How many times do I want to repeat it? Length of x. And that gives me a vector of zeros that's the same length as x. Okay? What's that going to be? That's going to be the counter. If something stacks, then it updates the counter. Okay? So I've got two vectors now. I've got x sorted, and then I've got this counter vector, which is zeros to start with. All right. Now what I'm going to do is I'm going to step through that x vector. Because it's been sorted, any time I hit a repeat, they'll be right next to one another. That's what sort does. It brings things into sorted order. So I go for I in 2 up to length of x. Why do I start at 2? Well, I'm going to compare an object with its predecessor. So if I start at 1, there ain't no predecessor. So I have to start at 2. So for I in 2 up to length of x, this is an example of a loop. So I'm going to loop through, and then inside the loop, if x at index I is the same as x at index I minus 1. So equals equals is a new operator. It asks the question, are the two things on either side of it the same? Okay. So if x at index I is the same as the one immediately before it, that means I've got a repeat. And if I've got a repeat, I'm going to update y, right? I'm going to update that counter. yi equals yi minus 1 plus 1. So if I hit a repeat, then it'll say, yep, xi is the same as its predecessor. I'm going to update the counter. So it'll go from 0 to 1. And if there's 2 in a row, it'll go from 0 to 1 and then to 2, right? Then I close that loop. Now, the last line in any function is the thing that you want to come out of the function, okay? So the last thing is going to be a list which has the x, the sorted values of x and y, the counters. Okay? So that's what stack does. It comes in, it pushes x into sorted order, it then runs along x and says, is this one here the same as the one previous? If it is, update the counter. If it's not, do nothing. Push on through, finish that x, okay? And what you end up with is the sorted x's and a bunch of counters. So that's what the function is and does. So let's have a look at this. Let's now plot the stack of inter and see what we get. Oh, we get an error. Why do we get an error? I don't know. Oh my God, look at this. In, do, try, catch. Oh my God. What's going on? Let's see. Maybe I've got a... Yeah, so that's what stack did. See how it's got all the x's in sorted value, and then it's got zeros, and then when it hits a repeat, it goes to 1. Okay? So why did that plot not work? Let's try it again. Well, that's what it looks like. Okay, that'll do. I don't know why it gave me that silly error. Okay, so you can see as you move along, x, and then all of a sudden, where you had a repeat, it jumps up. Now you can see the repeat. Now, this works all right, except that it only catches things that are exactly equal to one another, right? And sometimes you actually want to catch things that are just close to one another, not things that are necessarily equal. All right? So to make the plot a little bit more useful, I'm going to go over here and I'm going to change stack. Okay? So I'm going to come in and do the same thing. I'm going to sort x. I'm going to create my counters. And then what I'm going to do is, instead of checking whether x at index I is identical to the one immediately before it, I'm going to see if it's just close. Okay? How do I do that? I'm going to look at the absolute value. So I don't know why I've got caps lock on. Absolute value, xi minus xi minus 1. If that's less than some small number, so I'm going to put in what I call a tolerance, tol, okay? And in my function, I'm going to add an input, which is that tolerance, okay? So this is my new function stack. Just so I don't overwrite the old one, I'm going to call it stack2. So this is my new function, stack2. And what it's going to do is it's going to see whether not if x's are on top of one another, but if they're just close. And I get to say how close is close, right, by this tol thing. So let's run this, let's read this function in. Boom, there it is. Now I'm going to go back and do this plot. So we're going to use stack2 of inter. But now I need to put in this tolerance. Okay? So how close is the question. So if you put tolerance equal to 0, you get the old function back, right? So I'm going to put it something, I'm going to put it as 1. So that's pretty close. So let's see what that looks like. That looks the same as the other one. Okay? So 1 didn't really do the trick. So let's change that. Let's make it 5. Now see what's happening. Okay? These are all close to one another, and when they're close to one another, it starts to stack up. Right? And you can see that around here, they're stacking up about 5 deep. Okay? So I'm creating what's called a stacked one-dimensional scatter plot. Now, not particularly useful, but it should remind you of something. It's starting to look like a histogram, right? Bars that go up when data's close together. So we're sort of on the path of constructing our own histogram using this stacking idea. Now, after today, I do not expect any of you to ever use this function, okay? So don't go home and go, oh, I must understand stack. You don't have to understand stack. Today, the reason I'm talking about it is, well, there's a couple of reasons. The first reason is I want to show you how functions work. And this is not such a simple function that you could just write it. If you're learning R as you go, you probably couldn't write this function yet. I get that, okay? So this is just to show you how you can write your own functions. In this course, you're not going to have to write your own functions much, if at all, so don't worry, okay? But you can sort of see the power inside R because, I mean, this just came out of my imagination, right? I'm just doing stuff with this data It's not a function that already existed. So that's sort of a good thing. We also learned a couple of other things. We learned about how sort works. We learned about looping, a little bit of looping, that for loop. Okay? And then we also learned this key thing about functions, which you probably do need to remember, which is what happens in functions stays in functions. Inside a function, anything you create only lives inside the function, doesn't live outside. So for example, inside this function I've got a thing called x and a thing called y. Okay? X already lives outside, y only lives in the function. There is no y outside, right? So outside the function, unless I've already got a different object called y, if I type y, I've got a different thing called y already, okay? If I remove that, if I remove y, and I type y, it says there's no y, but the function still works, right? If I just go stack of inter, that y thing is created, right? But it doesn't live outside the function, see? Still gone. So, that's stacked 1D scatter plots. All right, so where are we headed with this? The idea is to use that second dimension to display something useful. And in this case, it displays how many points are close to one another in this distribution. So for the first time, we now can draw a picture of this distribution, right? You can sort of see it's sort of really skinny down this end, and then it starts to rise into a big heap, and then tails away at this end, okay? All right, so let's cut to the chase a bit. It should remind you of a histogram. So let's construct a histogram. In R, it's really easy. There it is. The main function is called hist, H-I-S-T, okay? And then you give it a title using main. I've got a subtitle, a label for the x-axis, velocity, a label for the y-axis, count. Col equals 0 says colour 0, so keep it black and white. Okay? All right. So, let's talk about this histogram. So this is the default. So R has a default for how many bins or how many little rectangles, okay? It uses a rule for that. All right, let's draw this histogram, you and me. So, you can see it on the screen, so now we're going to draw it with our fingers, okay? So, fingers out. And when we did this last time, if you've gone home and studied, you know how to get your finger out. Come on. Get them up, nice and high. All right, let's draw the histogram. Okay, let's draw the histogram. I'm going to watch you. I'm not going to draw it. So if you watch me, it's going to be no fun at all. So I'm going to watch you draw it. I'll start you off. Okay, go. That's fascinating. Okay. All right. So, okay. Some of you drew this. Okay. Right. So in other words, tail at this end, bump, and then a tail at this end, but a much shorter tail. Okay. Who thinks that's a reasonable description of this? Who thinks that's reasonable? Well, I do. Why is it not reasonable? What do you think the distribution looks like? Long tail on the left, hump, short tail on the right. Yeah? We good with that? Okay, cool. So you have a name for these shapes of distributions. Probably remember from first year. Skewed, right? Skewed to the left, right? So the left or right goes where the long tail is. The long tail's on the left, so skewed left. Okay? So, skewed left, tail on the left, hump at the right. Okay, cool. All right. Some of you drew this. You're literalists, right? You drew all the square edges. Okay. So this is interesting. I'll tell you why it's interesting, because who believes that that is what the actual distribution looks like? Does the actual distribution have edges? No, right? It's probably continuous, okay? So here we have a divide in the way people visualise things versus the way they actually think of things, right? If I ask every single one of you, do you think this is a discrete distribution? That is, it has bumps. Most people would say not a chance. Right? It's a continuous distribution. I just have data, right? But when you drew it with your fingers, some of you honoured that by making it smooth, right? And others of you drew the edges, okay? So that's interesting. Just tells us how different people visualise things in different ways. It's important to recognise that that is a thing, because when you draw a graph, you don't have much control over which type of person you're talking to, okay? So that's interesting. So we're on a pathway, of course. We're going to talk about histograms first, but then we're going to move to seeing if we can draw smooth densities. Because we really think smooth densities are nicer and probably a better representation of the data, okay? So that's where we're headed. Before we get to that, let's think about how we can mess with histograms. Because we just used all the defaults here. And the default gave me 1, 2, 3, 4, 5, 6, 7, 8, 9 classes, or 9 bins, okay? And I counted this one. That's a bin, that's a class. It just happens to be empty, okay? Gaps in histograms mean something. They mean a class or a bin that's got nothing in it, okay? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can change this. We can change this. I can go into R and I can go hist, except I'm typing in the wrong spot, thereby overwriting my file there. Let's go down here. Not there. Hist of enter n class equals, and I can tell it a number of classes. So let's do that. Let's tell it n class equals 5. Okay? Here we go. 1, 2, 3, 4, 5. Okay? Let's tell it n class equals 4. 1, 2, 3. So, guess what? R doesn't always give you what you ask for. Isn't that weird? Right? I can try 3. Still won't give me that. I can try 2. Oops. And it gives me 3. So it's doing its best. It's doing its best. I can try 1. Gives me 2. But if I ask for 9, it'll give me 9. Like it did before, right? So it sort of, the reason it does this, by the way, is that it sort of tries to get it right at the edges. And if there's one data point left over at the edge, it just puts a new class in, and that's so you get the number you ask for, generally +1, because of some rounding in R. And that's how it does it. So nothing really too much to worry about. The default almost always works, by the way, right? And this default tells you that the distribution kind of looks like that, right? Sort of tail on this side and hump, and then short tail on this side. Okay? But you can change what it looks like by changing this number of classes. If I put a ridiculous number of classes, you get that. So let me ask you a question. Is that good or bad? Bad. Okay. Here's a good thing about it, though. If I look at that, I can actually recover the exact data set. Okay? Because every data point is its own little spike, and if two things are on top of one another, it's all in that same spike. So I could use this to recover exactly the data. So this histogram, even though everybody in the room says it's bad, suffers 0 information loss. Okay? 0 information loss. Okay. What about this one? Good or bad? Bad, again. Maximal information loss, right? This would be like looking at this histogram through Coke bottle glasses. It's like I can see something there, it's a blob, but that's about it. Okay? This is maximal information loss. So what am I getting at here? When you construct a picture, you don't want to have no information loss. See, this is one of these things that people get wrong. When people go out and they take photographs, right, they want to get the absolute best focus, every detail, etc., etc. And you know that because the people who make cameras in phones, they just keep increasing the number of pixels and increasing the resolution, right? So at the moment, I think Apple's marketing calls their screen resolution retina. It's better than the human eye. Why? Who else is looking at it if it's not humans, right? Why are they making it better than humans? Not good, not good. So why do we want all that detail? Here's the thing. If you've got too much detail, you struggle to cope, right? You know this. Again, I go back to that silly one. If I say to you, what's the shape of the distribution, you start to not cope. You start to not be able to describe this in simple terms or even in complex terms. And if I say to you, use your finger to draw it, you're all over the place. You're drawing bumps everywhere, right? But we don't think those bumps are real. And so some level of information loss is acceptable. Too much information loss is unacceptable, right? And remember what I told you about statistics the other day. Statistics is all about compression. It's all about losing the information that's unimportant, keeping the information that's important, and then communicating that. And this comes through in the construction of a histogram. If you have too many bins, too many classes, what you're saying is, I don't want to lose any information, but that ends up being a bad thing because people then can't see the picture. Okay? And then on the other end, you've got too much information loss, and then it's just a blob. Okay? So these are difficult questions. The default works astonishingly well, but you've got control over that. So let's go back to the default picture. So that'll be just that one. Okay, it's got 9 bins. All right, now, here's something weird. When I got you to draw this with your fingers, pretty much everyone, either with corners or without, did this. Right? Right? Everyone started low on the left-hand side. Okay? But there's a bump here. Right? But people don't want to see it because people think, well, that's the tail, and tails don't have bumps. Right? There should be one bump. Well, we've got a strong preference for one bump. Because even if you drew the corners, you're still really, you sort of, at this end, you were low, right? So one question is this bump real or is it not real? And where might it come from? That's the question. Now, there are a couple of possible answers. One answer is it's just not real. It's caused by there being an outlier, right? Outliers happen. Now, how do you reckon they measure the speeds of these stars? And do you reckon it's an exact process? Probably not, right? So there's error in these measurements, no doubt. And so the fact that there's 2 data points out here that happen to be near enough to one another that they form a little bump is probably really just noise. And so most people go, well, it's noise, so I'm going to ignore it, and that bump doesn't exist. Okay? And that's probably a good call. So that's one possible explanation. There's another possible explanation, which is points out here, which are a long way from the rest of the data, maybe they aren't intermediate stars. Maybe they're a different kind of star. And maybe they're here they're not outliers in one sense, they're actually truly measured, but they represent different kinds of stars. So we've got those 2 potential explanations. And for those who came today hoping that I'd have the answer, well, guess what? Welcome to the world of being a statistician. I don't have the answer, right? How would I have the answer? I've never studied astronomy. I'm not going to go and ask Brian. He's busy, right? So I don't know. And this is a position that statisticians often find themselves in. Try and visualise data that you don't really have a deep understanding of. This is why it's important statisticians talk to other scientists. Okay? But even then, you might still have to make judgments around things like, is this bump real or not, through gut, essentially. So that's a question, is that bump real? All right, now what we're going to try and do next is we're going to try to move on from histograms by drawing smooth functions. As I said, there are a couple of reasons for this. One of them is because we probably believe that the distribution we're trying to visualise is smooth. Okay? We believe this data is continuous, and so we think it should have a smooth distribution. So that's one reason. The other reason is a bit more primal. You like smooth things. It's human nature to like smooth things. Okay? It just is. We like it when the road is smooth. We like it when the day goes smoothly. It's an aesthetic thing. Okay? And you might think to yourself, well, aesthetics aren't important to me. Well, they are. You put nice clothes on today, didn't you? Right? You might have put on makeup, you might have combed your hair. Okay, anyone just hop out of bed and come straight here? No, right? You cared a bit how you looked, because God knows someone might think, oh my God, that's awful, or whatever, right? So aesthetics matter. Aesthetics matter. And so aesthetics in graphics means smooth, okay? Smooth. All right, so I'm going to show you how R can draw a density. The basic command is pretty simple, but I'm going to have to go through it in some detail. The command is called density, so it's plotting a probability density. Okay? And so the basic structure is you go density, you give it the value for which you're trying to construct the density, inter. Okay? And then you tell it some other things. So window equals R, etc. So before I actually show you what it looks like, I'm going to do what you should always do when you're meeting a function for the first time. We're going to dive into the R help screen and have a look at that and see what is available to us. So, density. So it's short for kernel density estimation. That's kernel with a K, you know, like the little yellow things on corn, K-E-R-N-E-L, not kernel as in the chicken guy, Colonel Sanders. He was in some military thing, apparently. I don't know. Okay. What's the syntax? Density, you give it X. Okay. Then the main features are you go kernel equals, and then there are options, or you can go window equals. Window works as well. Windows is the same as kernel. See down here it says kernel, comma, window. So I'll tell you what that does in a second. And then you go width equals. So let me tell you how kernel density estimation works. And to do this, I'm going to draw on this whiteboard. They left a whiteboard in here, so I can draw on it. Isn't that cool? I should probably... but I'm recording the lecture, and that's not going to get recorded, is it? So, with that in mind... See, people leave bits of paper in here. I was going to try and use the document camera, so bear with me. That's document camera 2. Let's use document camera 1. So here's the... Ooh, that's very exciting. Here's the question. Will technology defeat me? Let's see. Document camera 1. Here we go. It's a scarily large hand. Okay. It's near the bottom. Put it up here. Wait for it to come. So here's the x-axis. Okay. Here's my data. So I've got a data point here, and This is like one of those trials where it says this is an artist's impression of the trial, this is my artist's impression of the data. Okay? This is what my data set looks like. Okay? So it's a line and there we go. Okay. So what's this kernel thing? A kernel is a little function, okay, that we're going to slide across this data from left to right. And the idea is that as you slide it across, you average the value of that function at the point underneath it. Okay? Now, I know it's not on screen anymore, but your choices for kernel are Gaussian. So these are your choices for kernel. Gaussian. So this, it looks like this. It's like a little normal curve. Okay? Your other choices are, well, there's one here called Epenichnikov. Which actually looks like this. It's like a little parabola. Okay? Then there's rectangular. That looks like this. Okay? And other choices are triangular, which looks, you can guess, like that, and cosine. And then there's a couple of others, but they're boring. So cosine looks like a cosine. So I draw the bottom in dots because you only take the positive bit. Okay? So each of these is a little function. Now, the way you think of these is as a blur. Okay? As we move this thing from left to right across the data, what it's doing is it's blurring according to that function. So if you've got a little Gaussian, the middle is sharp, but then the edges blur away. Okay? So think of this as a little blur that's moving across your data from left to right. If you've got 2 points under it, they accumulate. Okay? So, you start your little... I meant to bring some little transparencies along, and then I could do this live with transparencies, but I forgot. Maybe I'll do that tomorrow, eh? Okay, so here's your little... We'll start with a Gaussian. So here's your little Gaussian. It's here off the left, and what we do is we slide that across, and as we slide it across, it slides across this data point, and you get a blur on this data point. And then as you keep moving it across, right, at some point, it'll move off this data point and onto this data point, right? And it'll blur this one. Now things get interesting when you move down here. Because when you move down here, when it enters on this edge, you get this, but then it goes onto this one as well, and so you sort of get a double blur. And so this thing starts to stack up, okay? And so, and I'll show you in the notes what the function is mathematically in a second. But essentially, as you move into spaces where the points are close to one another, these little blurs start to stack up and you get sort of an intensity growing, okay? And so you just move it across from left to right, and as you go you keep track of where you're at and you build a picture. And in the end, it should look something like that, okay? And that's the goal. Now these different windows have different, or these different kernels have different features. Right? The Gaussian kernel is nice and smooth, okay? So think of this as a little window that's moving across, blurring your data. The Gaussian function is never actually zero. It gets pretty low, but it's never actually zero. So points blur in, up to full intensity, and then out gradually, okay? It's like when you go to a party and there's the guest there. You don't remember them coming, you don't actually remember them leaving, you remember in the middle of the party. There's sort of a blur, right? Like that. Rectangular kernels, quite different. They've got hard edges, right? So points enter and leave the window abruptly. So you get sort of spikier pictures, okay? Triangular kernels are sort of in between. They do have hard edges, but points enter and leave a bit more gradually, okay? So most of the time we're going to use the Gaussian kernel. It gives you the smoothest pictures. But I'm going to show you what the rectangular kernel looks like okay? And so you'll see the difference between these different kinds of kernels. So for most of us, most of the time, we're going to use the Gaussian kernel. It gives the smoothest pictures, okay? But I'll show you this one and this one as well. I'll show you all of them, but you know. So you've got two elements of this kernel. You've got its shape, and its shape governs the way the blur works, right? So if it's Gaussian, it's a nice smooth blur. If it's a rectangular one, it's sort of a harsher blur at the edges. It cuts off, right? The second thing these windows have is a width. And the width governs how big the window is, okay? Now, if the window's bigger, more points will get stuck inside it. So I've got control over this. I can make the windows really narrow, where points will enter and leave quickly, or I can make the windows big, in which case points will enter and stay in for a while, and then other points will come in while those initial points are in the window, and things will build more gradually, okay? So we're going to muck around with both of those things, okay? So that's how kernel density estimation works. For those of you, I know you can't see what I'm about to do, but that's okay. I'm just going to pop up a formula ready so that when I switch the screen you'll see it. So the formula that's going to be on the screen when it comes live in a second is the formula for a kernel density estimate. Where is it? There. I'm going to try and make it big so you... There we go. Okay, there's the formula. Okay, so what it's doing is it's taking a sum of the value of the kernel at whatever's inside it, okay, and then it's averaging those. So it's sort of taking a moving average of this kernel as it slides across the data from left to right. So that's the formula. If you don't care for formulas, don't worry, it's like it never happened. You're not going to have to use the formula because R does it all, right? So. Okay, so let's go ahead and plot the density, and I'll show you. So what I'm going to do in showing you is I'm going to leave off all the titles and stuff because it just gets in the way. I'm just going to show you the basic syntax. So, where am I? Here. So plot density of inter. Okay, so let's try a few different values for window and width. Okay. So I'm going to go window equals, we'll start with a rectangular kernel, and width equals a small number, 2, comma, type equals L. So type equals L says join the dots, okay? This is my first attempt. So it's using a rectangular kernel with a small window width, okay? So what's happening is that little window, that little rectangular window is dragging across, and as it drags across, as points enter, it spikes. And these spikes here, I know it looks pointy, but if you got close enough, you'd see the flat top, right? So it's just a resolution issue. And you can see where points are close together, the spikes rise, okay, because they're getting captured by that same window. So that's a rectangular kernel with a very small window. Let's up the window width. Let's make the window width 20 now, okay? See what's happening? Now you'll notice that it does have apparently flat bits. Okay, the top of that is actually flat. I know you can't see it, but it is actually flat. So what it's doing now is the windows are wider, so more points are inside the window at any one moment, and as you drag it across, this is what happens. Let's make the window width higher again. Let's make it 50. Okay, you can sort of see as you grow those windows, the blur gets bigger, and you're getting a picture of the data now. Let's make it 100. But even as long as I'm using a rectangular window, I'm going to have that sort of flat look to it. Even with window width of 100, it's looking pretty flat at some spots, and then probably 200 is about as big as I would go. And that's the picture of the data with 200, with a rectangular kernel. Okay? Now, what's interesting about this is, it's a question that must be occurring to you. Where am I coming up with these numbers? 2, 20, 50, 100, 200. Where do these numbers come from? The answer is, it's got to do with the scale of the data. This data goes between about minus 300 on the low end and about plus 100 on the high end. So that's a range of about 400 in total. Okay? So that range is sort of what my window width is relative to. So 2, which was my original window width, is tiny compared to 400. That's going to give me very spiky stuff. Okay? 200 is about half the range. So that's a big window, right? It'd be a window that's, well, it's about that big, right? About that big. And so if I make it really big, like silly big, 2000, everything gets blurred to hell. Okay? So it's just like histograms. If you choose a large number of bins, they're very narrow and you get a lot of spikes. If you choose a very small number of bins, they're very wide and you get everything blurred out. Window width works the same way in density estimates. When it's really small, you get very spiky pictures. As it gets bigger, you get very lumpy pictures. And the truth is somewhere in between. And rectangular kernels always give you that sort of flat top look. So they're not really a good choice if you want it to look smooth. So let's change it up and let's look at a Gaussian window. Again, a Gaussian window with a small window width. So it's window equals G for Gaussian. Okay, so R for rectangular, G for Gaussian. It looks pretty much the same, but if you could zoom in at the tops of those spikes, instead of being little flat tops, they'd be little Gaussian curves. So they'd be rounded off at the top. You could sit on this and it wouldn't hurt as much. Okay? I don't recommend sitting on any of this. Okay? Definitely don't sit on one with a triangular kernel. That'll break the skin. Okay, so width equals 20. Let's do the same thing. See how it's looking smoother now? Much smoother. Still too lumpy, but much smoother. 20 is not big enough. And we'll go 50 and we'll go 100. 50, starting to look smooth. 100, starting to look smoother. And then 200. And my best guess is when you were trying to draw this thing with your fingers, if you didn't follow the little square bits, that's what you were trying to draw. Except most of you didn't draw this bit, this bump out here. So we still have the question of is this bump real or not, but whatever. That's basically where we were headed, okay? Oh, what happens if I make it really too big? Guess what happens? You just get a Gaussian curve, right? In fact, so it does a maximal blur, and if you blur using a Gaussian filter, what do you get? A Gaussian curve. So I've blurred away all the real information and it's been replaced with the fake information, which is the Gaussian curve. Because these windows are my best blur. So this is just a picture of the blur function. Okay, and we could mess around with different ones. Cosine, well, let's do triangular. And triangular is sort of in between rectangular and Gaussian. So again, those are spiky at the top. 20 with window equals T. You can see they look spikier at the top than the Gaussian and so on. If I do 200 with window equals T, it's going to look all right, but it's probably a little bit spikier than the Gaussian. See how it looks that little bit edgier than the Gaussian one? Not too bad. And of course, if I go to width equals 2000, it's a picture of a triangle, basically. Okay? So, that's how densities work. All right, cutting to the chase. What do we do with all of this? Well, our goal was to draw a picture of this data, right? And so now we've got a bunch of tools that move us towards being able to do that. We've got histograms, but they're kind of lumpy, right? They have those sort of city block look. Now we've got densities, but we've got choices we've got to make. We've got to decide what kind of window to use And again, I think that's a pretty easy choice. I think Gaussian's a good general choice, so that's cool. But then we've got to decide on the window width, and that's going to be the critical thing. The window width is going to govern how many bumps you see, all right? So if I go back to Gaussian, because I think that's the right thing, if I use a width of 50, it's pretty bumpy.